Hello everyone, we've just finished talking about sparse linear regression, and we have almost all the ingredients we need to reach relevance vector regression. Let's just briefly recap all the design decisions that we have to make when choosing our regression model. We said that we can choose between a linear versus a nonlinear model. We said that we can learn the model parameters using maximum likelihood or maximum a posteriori or using Bayesian model fitting. We said that we can use our parameters in sort of the plain way, or we can use the kernel trick and focus on different models of kernels that we can apply directly without going through nonlinear transformations. And we've just talked about having weights for the full set of our model parameters versus doing so with a sparse prior, emphasizing some dimensions and suppressing the others to have, for instance, low or zero weighted phis. Now, we have one more important missing step, which is to talk about our model parameters either in the primal, which is what we've been doing, versus the dual domain. And so let's get into the dual linear regression model. With dual linear regression, we're looking at our model parameters phi, and we're thinking of them as actually being linear combinations of our data points. And you can actually see this in this figure. If we imagine that we have two dimensions for our data, the first and second dimension, so here model is the vertical and horizontal axes, we can think of our data points as lying somewhere in this space. So each red dot or yellow dot represents a point with some x1 and x2 coordinate. Now, slightly confusing if you look at our data points with a bold X and a subscript. That's actually indicating our second data point or our first data point. Now, if we think of our phi vector as being some vector inside of this space, this two-dimensional space, weighting our first and second dimensions, then you can see that any point on this plane can be expressed as some linear combination of our data points. And so if we try to reach a given point, like our model phi here, with this arrow coming out of the origin, you could see that that's simply the sum of two vectors where we've gone some distance towards x1, maybe not all the way, but some distance psi1 towards x1, plus some distance psi2 in the direction of data point x2. And so we can say that our model phi vector equals psi1 times vector, so representing data point x1, plus psi2 times our data point x2. And so in vector form, it looks like this. We say our phi equals our data matrix X, which is D by I dimensional. So it has D rows, one for each dimension of our observations, and it has I columns for I different data points. And so then psi is this vector that is I by 1. So it has one entry for every data point, and it's one column. The resulting phi, of course, is D by I, which is what we expected. But we've restricted ourselves to only move within the subspace of these points. So we can imagine some pathological versions of these points that don't span the space. And actually that might happen in reality as well if you have very high dimensional space because you captured lots of sensor data, but you also only collect data that spans a subspace, then you will never have a phi. If you use this dual representation, you'll never have a phi that moves out of the hyperplane spanned by your data points. You'll always just be reaching some linear subspace of your data points. Now in practice, that's not a massive limitation because it's very hard for us to do any kind of model fitting and decide that we want a phi that goes somewhere other than where the data was. Now that we've established that we can rewrite our phi vector in terms of a weight on our data points, so weighted by vector psi, we can go back to our original linear regression model and substitute it in wherever we see phi. And so that gives us our new dual linear regression model where the mean is x transpose x psi. It doesn't affect the covariance, it just affects our mean. When we try to learn our model parameters, we actually go back to the same maximum likelihood formulation if we like, and because of our substitution, we can solve in the same way, take the log derivative, solve for our model parameters, and we find that our maximum likelihood psi hat is x transpose x inverted times w. So we're using our labels and using our observations, and we also get our variance, basically the same formulation that we had before, just substituting in x times psi. If we multiply through, we can actually get from our psi maximum likelihood to our maximum likelihood phi. And it actually does work out. It comes back to the same thing we had because we've just done this substitution. There is, of course, the Bayesian approach to fitting the model, and it works out very similarly in that we can substitute in for all our versions of phi with x psi. And so when we rewrite, we have now a model with a normal distribution on psi, which we can express with a series of matrix multiplication operations. Now this is interesting because we now have a normal on psi, whereas previously our model was a normal distribution on phi. So far we haven't really changed very much, but our model is still expressed purely in terms of psi, and that transfers over when we're doing our predictive distribution. So if we're trying to predict our posterior for W star, everything is still in terms of psi. Notice that we're still just using combinations of x times x, whether that's the x star or it's our training data x transpose x, which means that the Bayesian formulation, even in the dual domain, is still amenable to the kernel trick. The other thing to note is if you wanted to have this be a nonlinear model, you could replace these x's with z's. Now, we're almost ready to do relevance vector regression. We have all of the ingredients, and so this is actually going to be quite simple. We're going to choose a nonlinear regressor. We're going to use the Bayesian formulation. We're going to have a sparse prior, and we're going to use our new dual representation. And here it is. We have done the nonlinear step. That was easy. We've done the Bayesian formulation. We've just introduced that. But the dual representation means that instead of having sparsity applied to our dimensions of x, we're now instead applying it to our elements of our training data. Basically, relevance vector regression is especially useful if you have fewer training points than you have dimensions d in your measurements. So in this figure, what you're seeing is the posterior distribution for W star given X star. And while we have a number of blue dots, only the big ones, the 6 big ones here, are getting some substantial weights applied to those data points. In other words, the model depends on those 6 data points and almost ignores or completely ignores the other data points. So if we look at the mathematical formulation of that, it is still a Gaussian process regression like we had it before. Of course, we've substituted for phi, right, to have our x psi. But now, instead of having a prior on phi, we have a prior on psi. Our sparse prior is still a product of student t distributions, one for each dimension. But now what that means is the dimensions are actually the instances of training examples, the I instances of training examples. So we have that many student t distributions multiplied together, and when we then plug that back in as our prior on our model, so our prior on our model parameters, we see that we can then have a normal distribution times our product of gammas. We still are going to have to iterate, as we did previously, do expectation maximization between updating our hidden model parameters h and our estimates of our weights psi. So when we're learning the relevance vector machine parameters, we can update our h elements this way, and we can update our variance parameters this way. Now, it looks slightly intimidating, but actually we've seen this before. If we recall, when we were doing EM learning of our model parameters for sparse linear regression in the primal domain, it looked exactly the same, except, of course, all of our subscripts were over the d dimensions. Now, we have relevance vector regression figured out, which is our combination of basically ingredients we've learned over the past 3 lectures. And now we're ready for some nice applications. The first one is body pose estimation, where we might choose to encode every image from our video stream as a 100 dimensional vector representing basically the silhouette of the person. Our aim is to regress a 55 dimensional W that represents the joint angles of this person. And we want to learn the relationship from a set of inputs x, so our vectors, and our outputs w. Now it's fair to ask, how would we represent our image or our silhouette of our person into a 100-dimensional vector x? And there are many ways, and of course later in the term we'll introduce convolutional neural networks, but let's go through shape context, which is a representation that was used successfully for handwritten digit recognition and for other applications, and was kind of a reigning champion for a long time. So after we have our silhouette, we can extract the boundary, and then we can resample the points on the boundary just by stepping along the edges. We want a representation, in this case a 100-dimensional representation, that's going to be fairly robust to small changes. So if some of the points on this A were to jiggle a little bit, we still want the 100-dimensional representation to be fairly similar. So the procedure in this case is quite a cookbook process. So you would center yourself on every one of the data points, the boundary points in turn, as we see in figure D, and you would place this sort of compass around, and you would add up the number of points in a given cell and write that down in these polar coordinates. So what you see here is the rows represent the distance from the center, and the columns represent the different cells along the boundary of the unit circle. So a cell that has lots of points in it, lots of boundary points in it, would then have more weight in this matrix. Now this is a 60 by 1 dimensional vector, and all it has done is sort of accumulated the information with respect to that one starting point on the boundary. And we have 400 such points, and we want to encode the variety that each of those 400 points feels that it has a different relationship with its neighbors. And so we can do this kind of dimensionality reduction by looking at our 60-dimensional space, right? Those are that's our log polar representation, and we can do a clustering. Now we have a choice. We could choose to find 2 clusters in 60-dimensional space or 20, but in this case, because we're aiming for an x vector that's 100-dimensional, we can find 100 clusters. And so we can then represent our space using this kind of Voronoi representation, right? The dual of the Delaunay triangulation. And for each of these cells, there are 100 of them. We could think about it having a boundary, and we can think of it having a centroid. This means now, once we've set up this representation based on a few training examples, we can now represent new silhouettes by looking at their encoding in this 100-dimensional space, as in we can see how many of each of these, how many of the boundary points lands inside of each of these cells, and we'd record that in the 99th slot out of 100. Of course, we have to train this model, and that means that we need for every silhouette a corresponding 55-dimensional vector representing the joint angles. Now, this isn't the last time you'll see a scenario like this, where it's actually potentially easier to create synthetic training data. So here you have a 3D mannequin that's taking on various poses, probably from a motion capture data set, and then we render just the silhouettes, and because we generated this synthetically, we know what the corresponding W joint angles are for this. In this case, when we use relevance vector regression, we have this sparse prior on our dimension of our training examples. We find that out of 2,500 training examples, we get by with only 6% of them being needed by our relevance vector regressor. In other words, it's ignoring 94% of the data because it has figured out that actually the 6% spans the space of what the model needs to do. And that has the impact that your regression model can now be quite simple. With just a handful of parameters, you can have a very fast regressor, which then is able to estimate our W for each new silhouette. The result is actually an average error of 6 degrees on each joint angle, and in this case we've treated each of the dimensions as the output dimensions W as independent. So we've basically done everything we did previously, where we were regressing a single value of W, but we've regressed 55 versions of W, one for each element of the joint angles. Another nice example of using relevance vector regression is for tracking. So we might start off with an initial frame where we see a person's face in its entirety. But we could very quickly, behind the scenes, train a relevance vector regressor by simulating a shift of the face relative to the camera, either to the left or the right. And because we've simulated the shift, we actually know how many pixels we've moved left or right, and we can say that this appearance matches the person moving their head, for instance, to the left and having one of their eyes cropped. With a number of training examples like that, we can do regression in 2 dimensions, representing translation in X and Y. And we can then simulate occlusions so that when we come to test time, actually the tracker is robust to having part of the face occluded using cards or any other kind of obstacles. The other little trick about this tracker was that you don't have to just use the original image. You could actually instead look at an edge-detected version of it. So basically filter it with an edge-detecting kernel, and now it's the image gradients that are important to the relevance vector regressor, and that means that it actually is quite robust to lighting, so illumination changes. So let's recap. Regression still isn't used as much in computer vision as classification, which we'll talk about next time, but it has all of the necessary ingredients, and in this way we've gone through and introduced the idea of having nonlinear functions, the kernel trick, the dual representation, and sparse priors that we can apply, either sparsifying the weights on our dimensions D or on our training examples I. We've introduced the relevance vector regressor, which you can compare and think of as the probabilistic and Bayesian version of support vector machines, which will come into play again when we get to classification. All right, thank you, and see you next time.